folks, welcome back. Let's take a look at how the process changes slightly when we have repeated linear factors. So our denominator can still be broken into linear factors, but we might have something repeated like x plus 1 squared, x minus 3. So what do we do when we have a factor who's got a multiplicity larger than 1? Still linear, right? Each of these factors are still 1, but this one's got an exponent. This factor of, oops, sorry, I just realized I wrote a 2 there. This should be a 1, right? So these are linear factors, and that x is raised to the first power here, but this has got a multiplicity of 2. So in order for partial fraction decomposition to work, we have to just tweak what we did before slightly, but we still need the degree in the numerator to be strictly less than the degree in the denominator. So what we do is we'll go ahead and we'll set up a fraction for each degree of this repeated linear factor. So I'll set a sub 1 over ax plus b, a sub 2 over, you can see here, ax plus b squared, then ax plus b cubed, all the way up to ax plus b to the n, and we'll do that for each linear factor. So what I mean by that is, let's say I'm just going to make this up, right? So let's say I had that 5x plus 16 like we had in the previous example, and my denominator now was x plus 1 squared, x minus 3. What I would do is I would set up a linear factor for x plus 1 to the first power. I would set up another linear, or I should say another fraction for the second degree on x plus 1, and then I would set up a third one for x minus 3. So take note, each of these are linear factors. This one is squared, but because this is a linear factor, we have a constant up here. Linear factor, constant, linear factor, constant. But I do have an extra fraction represented for that repeated linear factor with x plus 1. And that's the mechanics for how to get partial fractions to work when you have a repeated linear factor. So let's scooch this up and take a look at what we have in example 3. All right, let me scooch this all the way up. There we go. We're going to need all the space we can get. And let's go ahead and work this with that repeated linear factor. Okay. So what I'm going to do here is I'm going to take 6x minus 11. All right, and I see x minus 1 squared. This has already been factored. And if you're thinking like, well, what could it also have looked like? This is ultimately x squared minus 2x plus 1. So I want to point out that the degree in the numerator is 1 and the degree in the denominator is 2. We can see that in that there's an x squared. So I could have started this problem giving you this is the denominator, asked you to break it down into that repeated linear factor, but here we are. So what I'm going to do is I'm going to write a fraction, and I'm going to have a fraction that represents each degree of this repeated linear factor. So I'm going to have a over x minus 1 and then b over x minus 1 squared, right? And if this had been cubed, I know it's not, but if this had been cubed, I would have had c over x minus 1 cubed, right? If this had been to the fourth, I would have added a d over x minus 1 to the fourth. So you add a fraction for each power of your repeated linear factor. And then from here on out, everything's the same in that I've got an equation with fractions. I want to get rid of these fractions. So I'm going to multiply everything by the LCD of x minus 1 squared. I'm going to multiply the left side of the equation by that. I'm going to multiply the right side. And when I multiply x minus 1 squared to the right side, I'm going to multiply it to both terms, right? I'm going to distribute. And if we multiply the same term to the left as right, I get to keep the equal sign. So let me start to write this out. LCD times the left side. And then that's going to be LCD times the right side. And I'm going to distribute. And a bunch of fractions are going to disappear by design. That's what we wanted. So if we take a look at that, I can see that my entire my repeated linear factor cancels, right? Here my repeated linear factor cancels. Here I've got x minus 1 squared, and I've got just an x minus 1. So the denominator will cancel and leave x minus 1 to the first power on that numerator. So if I take a look, and actually I'll make a new line just so that we have plenty of view space. On the left side, the only thing that survives is 6x minus 11. On the right side, I've got a times x minus 1 plus b. All right, and here's where I'm going to go ahead and distribute a little. And then I'm gonna collect like terms. I'm gonna set up a system of equations. So I've got 6x minus 11. That's gonna be ax minus a plus b. Now, if you wanted to, you could start plugging in values of x, and I can show you that version a little bit later. I think in this case, it might actually be a little bit faster just to set up your system of equations, because here you can see on the left side, I've got a 6x, and on the right side, I've got an ax. And since those are my only terms with x, I know a has to equal 6. It's got to line up. So that's kind of nice. Ooh, that's a funky looking a. That's kind of nice in that a equals 6 right away. I can spot that. And then my constants are negative a plus b on the right and negative 11 on the left. So I know negative a plus b has to equal negative 11. And if a is 6, we've got negative 6 plus b has to equal negative 11. And when I add that 6 to the left, like when I move that 6 to the right side, I'm going to get b is going to be negative 11 plus 6, which is going to leave me with negative 5, right? Which is great. I've got my a value, I've got my b value, so I'm almost done with this entire problem. If I want to go ahead and write up my solution here, I will say that 6x minus 11 over x minus 1 squared, right? This is what I was starting with. I'll put the little therefore to be fancy. It's a over x minus 1, so that's 6 over x minus 1. B was negative 5, so I'm going to write minus 5 over x minus 1 squared. And if I wanted to check my work, I could take these two fractions, find my LCD of x minus 1 squared, subtract them, and I should get back to 6x minus 11 over x minus 1 squared. Okay, I want to show you one other way that I could have found 6 and negative 5, the plug-in way. So let me go back to this step. And let's try the plug-in way. Here, let's let x equal 1. All right, I'm going to plug in a value for x, and I'm going to choose 1 because 1 will knock this factor out. So if x is 1, I'm going to have 6 here, right? 6 times 1 minus 11 is going to be negative 5. If x is 1, 1 minus 1 is 0. A times 0 is 0. This goes away by design, and then I get equals b, right? And that's great. So I get b equaling negative 5. The only issue here is that there's not really another great x value to plug in, right? I don't really have, because there's not like an x minus 2 here, so I could plug in 2 and knock that out, right? I just don't have that in this case because I had that repeated linear factor, and that's different from what we saw in example 2. But don't fret, you can plug in any value of x. So I'm just going to try x equaling 0. If I let x equal 0, I get negative 11 on the left side. If I let x equal 0, 0 minus 1 is negative 1. Negative 1 times a is negative a plus b. But we know b is negative 5, right? So I can start to sub this, and I get negative 11 equals negative a minus b. When I solve for a, right, and when I know I'm getting to the end, let me scooch this up just a bit. If I solve for a, if I add 5 to the left side, I'll have negative 6 equaling negative a, and I still arrive at a equaling 6 and b equaling 5. Oops, you can't quite see that. There we go. So the plug-in way works, or you can set up a 2x2 system of equations. Totally your call. All right, thanks so much, everyone. Bye.